Hello and welcome back. Let's dig right into Chapter 5. Chapter 5 is when we start to go into this idea of control structures, which is so essential to computation. But let's step back a bit and see what the story has been so far, right? The story so far is that, well, we started by looking at this idea of processes. And these processes were things that transform data to information, and we realize that that process is an algorithm. We saw in the first few chapters where we looked at the data's temperature values, and the process was to average and threshold them, and then from that we got the information, which was, is it cold or not? And that algorithm we called a step-by-step procedure, and it consists of these control structures, which we're going to dig into, and the control structures control the flow of execution of the algorithm. And you sort of see this process outlined down here where we talk about the overarching theme, which is the transformation of data into information to knowledge. And that transformation is controlled by a process. Now we're digging into the guts of that process, and we're going to see and explore this idea of control structures and the flow of execution in our programs. So what exactly are these computer programs? Well, a computer program can be thought of as a detailed, step-by-step sequence of instructions that tells a computer what to do. And if we change the program that we ask the computing agent, in this case, the digital machine, the computer, to execute or to carry out, the computer will end up performing a completely different set of actions or completing a different task. So the program is specific for the task that you want to handle. And if you change the program, you change the task that you do or handle. The machine stays the same, but the program changes. This is the idea of a changeable program rather than getting a brand new machine, which we did before the advent of these general purpose computing machines, which we talked about with Babbage in the 19th century and prior to that as well. So now that we have these digital machines, the programs that we write contain instructions that have to be eventually carried out or executed by the CPU, the central processing unit. So all of these program instructions that we write in some higher level language, like Python, for example, eventually have to be translated into binary, because binary is all that the CPU, the central processing unit, understands. The reason is that the CPU consists entirely of these switches, in essence, right? In the abstract, we can think of it that way in this first approximation. These switches then can be combined and used to create more complicated functions. So functions such as Boolean circuits, which we see over here, like an AND switch. In this case, the flow of electricity goes through the circuit when both this switch and this switch are closed. Or switches. In this case, the flow of electricity comes through this circuit if either this switch or this switch is closed. And these are the functions that we then combine to carry out basic operations on data, things like the arithmetic operations, the memory operations, all of that stuff where the CPU interacts with the memory. And so the memory, the CPU, and the instructions all come together in a certain architecture or in a certain specific structured manner. And a computer's memory, the way that it's organized, contains both programs, that's the instructions, as well as the data that the instructions operate on. This kind of architecture, this kind of structure is called the von Neumann architecture, after John von Neumann, who first, well, he wasn't the first to propose it. It was also in Babbage's approach and in some of the prior ones that we saw in the historical aspect, but he brought it to fruition. John von Neumann was, of course, an absolute genius who made a lot of contributions to many fields. And when he first started working on these machines, these computers that are modern computers that we might say, he sort of proposed this idea of putting programs and data in the same memory space, into that main memory. One of the reasons is that the different kinds of memory that a computer has is main memory and secondary memory. And main memory is very fast, but it's volatile. So if you unplug the machine, all of the contents of the main memory go away for the most part, right? There are ways around that. And then there's secondary memory is persistent. It offers more permanent storage, things like magnetic storage and optical storage that you might have. The CPU only has direct access to whatever's stored in main memory. That's that random access memory, which it can access. And so from that main memory, it gets both the instructions and the data. So it gets both of those entities from that main memory, from that RAM. And it gets that and then processes those instructions on that data. It does all of this in what's called the fetch execute cycle. So the CPU utilizes this fetch execute cycle. And what that involves is fetching or retrieving the instruction from memory. The first time through would be the very first instruction. So it knows, the program counter knows exactly where in memory that instruction is. And since it's in binary and data and instructions or programs are stored in the same memory space, it's contextual. It's the context determines what a particular bit or a particular byte refers to. This is similar to in the English language. If I said two, you wouldn't know if I meant the word TO or if I meant the word TWO. And you determine that based on the context that we have, right? And of course, there are not just these homophones, but there are also other words that are even spelled the same but mean different things. And most natural languages have these kinds of words, and it depends on the context what you intend. And the same thing applies with this binary representation of both data and programs. Which bit does this go, which sort of thing does this bit go with? Which thing does this byte go with? It depends on the context. So assuming the context is resolved, the first thing the CPU does is it goes out and fetches or retrieves that first instruction from memory. Then it decodes that instruction and figures out, what is this instruction telling me? And once it figures it out, it carries it out or executes that instruction and the action that is determined by that, the appropriate action that it says. And once it's done doing that, it goes and fetches the next instruction, it decodes it, and it executes it, and it keeps repeating this endlessly while it's on, or you tell it to shut down in some way, right? That's what the CPU does. So it's a very simple machine, and it does very simple operations, but it does them very fast. Clock cycles on these modern machines are super duper fast. But that's essentially all that the CPU does. And it makes sense because most modern computers will follow the same kind of prescription. The programs are the instructions for the computer to execute or carry out. So we can say that a modern computer can be defined as a machine that stores and manipulates some information or data, or properly, under the control of a changeable program, right? The machine stays the same, the program is what changes. And so these key elements that you can sort of derive that we utilize in these modern machines were these elements that were actually noted even earlier by people like Turing and some of the founders of computer science. And that is that a computer is a device, it's an agent for manipulating information or data, and that computers operate under the control of a changeable program. And we usually follow the von Neumann architecture where the data and programs occupy the same memory space. And so as you start to generalize this idea of a computer, one of the things that you end up with, or any kind of computing agent, is this idea of the Turing machines that we saw earlier. Remember when we saw in 1936, Turing was trying to figure out, well, what does it mean for something to be computable? Or what do we mean when we say a task is computable? And there's the intuitive idea of what's a task being computable, which is that, well, you specify some sequence of instructions which will result in the completion of the task. Usually it's to solve some function that we have, right? Some mathematical function. And that's what Turing developed in a more formal way. He proposed a whole class of devices to start to formalize the notion of computation. These were the automatic machines that he created. We now call them Turing machines in his honor. And of course, it was very interesting because he was able to reformulate Kurt Gödel's 1931 results on the limits of proof and computation, but he replaced Gödel's universal arithmetic-based formal language with just these very simple hypothetical devices that he'd proposed. And what did these do? Well, the Turing machine did the same kind of thing that our digital machines do nowadays. They have some programs, and the programs are executed or carried out by the Turing machine. It operates under some program or a sequence of instructions. This is the same thing that digital machines do, right? All programs, in fact, all computers, in fact, have the same power as long as they have the suitable programming. So whatever one computer can do, any other computer can do, as long as it has this what we'll talk about, this minimal set of operations and instructions. Then they can all do it, and we call such a computer Turing complete, because whatever, if a Turing machine is a very simple machine, right? All that the Turing machine does is it does three things. It can write and delete a symbol. And remember, it was this sort of like this ticker tape with a little head that could move back and forth on it, and then that head could then write or delete a symbol, and then you could move the tape head left or right on this ticker tape. We talked about how the model that they used was derived from the technology that was at the forefront at the time, and it was these ticker tape that these stock brokers used, and it basically fed in the symbols and the prices for the different equities they were tracking. And of course, there were these reams and reams of small tape, small paper tape that was produced. And so when there was a parade, they dumped that out, and that was the ticker tape parade, because they had all these reams and reams of small paper tape lying around their offices because these machines were clicking away all day long. And that's what sort of Turing essentially modeled over here. And then so the Turing machine can write or delete a symbol. It can move the tape head left or right, and it can go to a new or stay in the same state. So any machine that has this sort of minimal set of operations can do what a Turing machine can do. And since a Turing machine is the definition of computation, anything that can be computable can be calculated by a computer, any Turing complete computer, as long as you have enough temporal and spatial resources, time and memory, that available to you for that. And we talked about this idea of what's tractable versus intractable earlier as well. And so it turns out, just like the Turing machine had these certain operations that it could do, for most modern digital machines, there's a minimal instruction set for the CPU that's required in order for it to be able to carry out these things. And there are different numbers of instructions that are considered minimal or fundamental for such an instruction set. You can actually even come down to one. But in general, the 5 instructions that are listed here are the main things that it needs to be able to do. It needs to be able to load the contents of RAM, right, from some address that it has, and this is looking at the version of not binary, because remember, binary was the first machine language, that was the first generation, but a second generation assembly. So not only can you load the contents from RAM into your accumulator, but you can take values that you've calculated or have in your accumulator and store that into RAM as well. Then you can clear this accumulator, you can increment it, and then here's the magic: branch to a different address if there's some value in the accumulator. So you can take this and change where you go, to which address you go. And so this instruction, it turns out there's something kind of magical about that. It's this control that it has. It controls where the instructions go. And it turns out there's as we look at these higher level constructs that we have. There's a certain theorem in computer science called the structured programming theorem. It's also called the Bohm-Jacopini theorem, and it's a result in programming language theory. And it says that there's a class of these control flow graphs, and they used to be called charts in this context, that can compute any computable function if it combines these subprograms in only 3 specific ways. And those ways are these control flow graphs, or these control structures that we're going to call them. So by way of preview, I'm going to give them to you now, and then we'll delve into this as we go on, of course. But they are basically executing one subprogram and then another subprogram right after it, and continuing in a sequential fashion. So one of the ways that you have the flow of control is just in a sequence. Then another is sort of what we saw with that branch Z. When you execute one of 2 subprograms, say they live at 2 different addresses, according to the value that you might have. And we'll talk about what this value is, whether it's a Boolean expression or not. Why should it be a Boolean expression? Because we had that branch if 0, for example, that we looked at just a minute ago. But this kind of control of the flow of execution is called selection, because you select between one of 2 subprograms. Then you could also repeatedly keep executing a subprogram until some condition is met, until some maybe Boolean expression evaluates to true. And that's called repetition or iteration. It's used synonymously, sometimes called looping as well. There are a lot of synonymous words that are used for that. All right, so let's step back and sort of examine the story that we have so far before we delve into these control structures and sequence selection and iteration in more detail. So we know that when we write a program, what we have is a computational solution. That's what a program is. Solves some computable function, and it's made up of a sequence of instructions. So this sequence of instructions is expressed in some high-level programming language, like Python, for example, rather than in the low-level language that the CPU speaks. Since the CPU is made up of a bunch of switches, all that it speaks is binary. So the instructions that you have in this high-level programming language, these instructions have to be converted to binary so that the CPU can execute them. It can pipe them through its switches and then come up with a result and pipe that back to you, binary, which is then converted back into that higher-level language that you saw. And so we also see that it's possible to construct some minimal instruction set at the lower level of the CPU. And that's what we saw with the assembly a little while ago as well. And that minimal instruction set was sufficient to express every possible program or computational solution. Because it's Turing complete, and that means it can solve whatever problem a Turing machine can solve. And so something is a problem or a function said to be computable if you can find a Turing machine for it. So anything that's possibly computable can be computed by any Turing complete machine that you might have. And so these control structures that we have, that minimal instruction set, also leads to this idea of these controls structures that can help us determine the order in which a program's statements are executed. And so this is what we utilize over here, as long as you have the appropriate storage for the variables. And so the 3 structures that we utilize are the sequence structure, the selection structure, and the repetition structure. So what exactly do we mean by these control structures? What exactly is a control structure? Well, the control flow is the order in which instructions are executed in a program. And so the control structure determines the control flow of a set of instructions, how they flow, in which order should you execute them. And a control statement is how a particular language implements that control structure that you have. For example, we saw these 3 fundamental control structures: sequence, selection, and iteration. So all languages implement these control structures using control statements that are peculiar or particular or idiosyncratic for them. They have similarities, and so most of them offer the same kind. Most languages nowadays, higher level languages, offer the very similar implementations of these constructs, but there are variations. But these are the fundamental forms of control that programming languages provide. So what exactly are they? So in sequential control, I know we've looked at the Reverend Zeller algorithm before, but another way that I might say we can look at it is the sequence of order that the instructions are executed. Suppose you're giving directions to your house to a friend, and you tell them, go 1 mile and then turn right. So the instructions are very simple. Go 1 mile, then turn right. But the order of instructions is very important. If you were to flip them around and you said turn right and then go 1 mile, you end up at a very drastically different place. That's sequential control. The order in which the statements or instructions are executed is very important. That's that sequential control that we have. For selection control, what you might want to think about is the Robert Frost poem, The Road Not Taken. Right, in this, there's a traveler and he's going on a path and he sees the road bifurcate into two different paths. There's a left path and a right path, and he has to decide which path to take. Now, the poem has some interesting complexity to it, and it's often misinterpreted, but for our purposes, it's that decision that you have to make. You have to select one path, either the left path or the right path. How do you make such a selection? Maybe it depends on how adventurous you feel. So when you get to that fork in the road where it splits, you might pause there and ask yourself, do I feel adventurous? And depending on your answer, if you feel adventurous, then you'll select the left path. If you don't feel adventurous, then you'll select the right path. That's the flow of control that you're changing. You're selecting one of those paths. That's the selection control structure. And for iterative control, the easiest thing to imagine is how you're doing dishes, right? We've all worked as dishwashers before, either in a professional or a non-professional setting. And how do you do dishes? Well, you usually have a stack of dirty dishes, and so you grab the first dirty dish, you wipe it off, rinse it off, soap it up, rinse it off, dry it off, and put it on the drying rack, right? And then are you done? No. What you have to do is then grab the next dirty dish and repeat that process again. Getting the food off, rinsing it off, soaping it up, rinsing it off, drying it off, putting it on the drying rack. And how long do you compute this? Or how long do you keep repeating this action? Well, you keep repeating it as long as you have dirty dishes, right? So as long as that stack of dirty dishes isn't empty. So every time you finish doing a dish, you ask yourself the question, is that stack of dirty dishes empty? And the answer will be either yes, it's empty, in which case you stop repeating that action, no more dishes to wash, you go on and do the next task, or no, it's not empty. That means grab the next dish, we're still working away, right? That's the iterative control that you have. And all of this changes the flow of control. So you know that we come up with these computational solutions. It's represented by our algorithm. In some sense, it's implementation of our algorithm. Other times, the algorithm can represent that. But in the end, that computational solution is finally then, or algorithm is then implemented as a program which consists of multiple instructions or multiple statements that will eventually solve the problem. And so the order of statement execution is called the flow of control. And these three fundamental control structures, sequence, selection, and iteration, control how that flow moves. And so unless you specify otherwise, it'll always be sequential, right? The order of statement execution is always going to be linear. It's always going to follow it in sequence. The order in which the statements are presented, that's the order in which it'll be executed, unless it's specified otherwise. So by analogy, you can think of Newton's three laws if you really want to sort of make that torturous analogy. So you can say, the motion is uniform linear motion. That's Newton's first law of motion, unless acted upon by some net external force. Similar sort of analogy. So how do you specify otherwise? Well, the way you specify is you allow it to either make a decision by selecting one or the other option, right? Or maybe more than one, but let's just stick with one or the other option in this case. We can have more complex decision making later on. But you select one or another option, a selection, or you repeat an action multiple times. And it turns out these decisions for both the selection and the repetition are based on Boolean expressions. They're either true or false. Let's look at another example of this thing. How is it Boolean? Well, maybe you're hungry, right? Maybe you're sitting there and you're getting a little hungry. And so you ask yourself, hey, am I hungry for Pizza Hut? If the answer is yes, you go get Pizza Hut. If the answer is no, then you go get Burger King, of course. Then once you get to Burger King, maybe you decide I'm not hungry for pizza, so you're going to execute the Burger King function. Then you can ask yourself, am I hungry for a Junior Whopper? You might be getting some insight into my fast food habits, but maybe that's a question you ask. And the answers, the possible answers to these questions, each of these questions, are Boolean answers, yes or no, true or false. Am I hungry for a Junior Whopper? Yes, I'm hungry for a Junior Whopper. Great, order the Junior Whopper. No, I'm not hungry for a Junior Whopper. Fine, order the Double Whopper. Stop twisting my arm, right? So these control structures that we have, these three fundamental control structures, can also be represented in the Unified Modeling Language, UML. And so they're usually expressed something like this, where you see sequence as one, you come into this little block of instructions, and in the sequential control structure, each instruction is executed one after the other. There's no jumping around, there's no branching that's occurring. In selection, like we saw in the Robert Frost poem, you have to make a decision, and that decision is represented usually by a diamond. And the decision is where you ask a question. The answer to that question is Boolean, true or false. If it's true, you execute this instruction and skip the other one entirely and then continue on. Or if it was false, then you execute that instruction and ignore this one completely and continue on. And iteration or repetition, where we did the dishes, remember that? Similar form. You also make a decision, again, represented by this diamond. And if the answer is true, hey, do I have any more dirty dishes? Yep, continue doing it, continue doing it, continue doing it. When the answer becomes false, nope, I don't have any more dirty dishes, then you can carry on and do whatever you were going to do. Now, these are all controlled, as I said, by Boolean values. These are the yes-no answers that we talked about. And I know we've referenced this previously, but this was developed by George Boole, who wanted to give an algebraic framework for syllogistic logic, the same way as Descartes had given an algebraic framework for the geometry in Euclid's Elements. George Boole was this deeply religious guy who wanted to know the mind of man, and he assumed that logic, specifically Aristotelian logic based on syllogisms, was the basis for the mind. This isn't that striking. We usually end up using whatever the most current technology is as a model of the mind. We find that in neurobiology constantly. When we had the telephone first come into play, people imagined that the mind was like a telephone operator where you connected different lines. Now we have digital computers. We say, oh, the mind must be like a digital computer, right? So the mind is like a computer. Similarly, back then, he assumed the mind was doing logic like the current state of the art at the time. And so it was very interesting when he did this in the 19th century, but its utility really came to the forefront when Shannon started to look at logic circuits and the design of logic circuits and found this correlation between Boolean algebra and Boolean operators and these logic circuits that were starting to come into play in some of these digital machines that we have. So anyway, there's a nice little background and history on that. We've sort of alluded to that before. And so let's delve back into exactly what these control structures, would be for computing agents. Some of these control structures we talked about, the examples that we're talking about, are mainly in the context of human computing agents. And remember when we looked at the Reverend Zeller algorithm, we did the same kind of thing, and when we were computing the day of the week. So for digital computing agents, these digital machines that we utilize nowadays, each language provides some implementation of those three fundamental control structures: sequence, selection, and iteration. So in Python, for example, we can implement the selection control structure as certain control statements: the if-else control statement or the if-else-if-else control statement. Let's take an example of that in some detail at this point. So the way Python implements selection is by using the if control statement, and the general syntax of that is over here. If some Boolean expression is true, you add a colon, then you execute the statements that are indented, and that indentation is very important. Else, otherwise, colon, execute some other statements. And so the first line is called the header. That's the if part. And normally you'll enclose that Boolean expression in parentheses, just like we see here. Then you'll add a colon. And then all of the statements that you have, those statements are considered the body of that control statement or control structure statement. All of those statements that belong in the body, they have to be indented. Python relies on indentation to indicate belonging, so that it knows that all of these statements go together in that control structure. And then as I'd mentioned, we also have these more complex constructions that you can do, which we call compound statements, where you can have more complicated logic. If Boolean expression A is true, then execute this bunch of statements. Else if, otherwise if Boolean expression B is true, execute these other statements. Otherwise, else, colon, execute this bunch of statements C. Now, the important note here is that only one of these sets of statements is executed. Either statements A, statements B, or statement C. Not all of them. You're selecting between one group of statements. Now we know that indentation is very important in Python. It's a unique aspect of Python. It's one of the reasons why it's very popular and beloved, and also one of the reasons why it's looked upon unfavorably as well by people coming from other languages where they have other habits that they sometimes need to break. Right? So the indentation in Python is very significant. In most programming languages, indentation has no effect on program language. When we'll look at Java, for example, we'll see that what belongs within a certain structure is explicitly delimited by these curly brace delimiters. So you explicitly state what goes within it by using these explicit delimiters. Not so in Python. In Python, it's the indentation that's implicitly tells you what belongs within a certain construct or doesn't. It's used to sort of align program lines and also to aid the readability. In fact, you'll still do that in other languages like Java, where the white space or the indentation is ignored. You'll still align it in a nice way and format it so it's readable, because maintenance ends up taking up a majority of the cost of any significantly complex project for the most part. So you want to make sure it's readable so it's maintainable. Either you need to do bug fixes or extensions, feature extensions, etc. But in Python, indentation is used to actually associate and group statements together. And so these statements that we've looked at, like the selection statement, remember we had this thing where there's some Boolean expression. Well, you can have some pretty complex Boolean expressions. That Boolean expression can be something that evaluates to a Boolean value. So it can utilize any of these relational operators like equal to, not equal to, less than or equal to, etc. Or it can also utilize some of the Boolean operators or logical operators that George Boole had developed. The AND operator, the NOT operator, or the OR operator. And you can combine relational operators with Boolean operators to implement some rather complex logic. And in the end, all of these operators and all of these expressions will evaluate to a single Boolean value, true or false, because that's what the selection has to evaluate in the end. The selection statement, the decision that you make, the condition that you have, has to in the end evaluate to a single Boolean value, true or false, and that's what it does. Now we said that the other construct that we talked about, we had sequence, we had selection. The third most important part was the iteration or the repetition. Well, there are a couple of ways that Python implements that. By the way, the selection can be implemented in multiple ways in other languages. In Python, it's simple and it's just that one way. But iteration can have multiple. The iteration control structure can have two different control statements. Iterative control statements that you can use to carry out iteration. It can be the for control statement, or as we'll see, the while control statement. Both of those control statements are utilized for iteration. One lets us construct definite loops. These are loops that go on for a certain amount of time that you know ahead of time how much they'll be at the time of execution of the loop. Well, there's some subtleties that we'll address later on. And so the for control statement provides a very convenient way of iterating over lists and other sequences that you might have. Its syntax is again rather simple. It says for, and then there's a variable that's created here. It's the loop variable. So for e, and you can call it whatever you want. Let's just say for e, and the way that you think about it is you'd say for each item in some sequence of items that you might have. That could be a list or some other sequence that you create. Execute this bunch of statements, right? And so this provides that iterative control that we need, and sometimes called loop as well. And so we can see it in action. So we can say, for example, suppose we have a list of the numbers 1 through 10, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We can say for each number in that list, and there's a colon. And then, of course, remember each statement that you want to execute, you indent it. You can maybe add to total. You can maybe do a summation. Isn't restricted to one statement, just like with the if selection. You can have multiple statements that you can execute in there. Then a function that's utilized often in Python is the range function to specify a certain number of times that some operation should be carried out. So in this case, it says for each number, and each number is the loop variable that's created locally and used locally and destroyed after you exit that loop. For each number in range from 1 to 11, so it'll do that same thing. It'll create the same list, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, starting at 1, ending at 1 less than the last item in there. It'll do the same thing. It'll sum plus each number will add it in. So both of these loops end up doing exactly the same thing. And you know how long they'll do it. They'll do it for 10 repetitions. That's a definite loop. Indefinite loops is where the number of times the loop is executed isn't specified explicitly in advance. And you implement these using the while control statement. Looks very similar. In this case, you say while some Boolean expression is true. Right? Whatever that Boolean expression might be, execute the statements that go inside that construct. And the construct depends on some loop variable n. That has to change. Otherwise, if it never changes, let's say that Boolean expression starts off as true, say n equals 1, and the Boolean expression that you utilize is n less than or equal to 10? Yep, it is. So then I'll start to execute these statements that are in here. Now, if n never changes, then this loop will continue forever, and you'll create what's called an infinite loop. And so you more than likely don't want that. Sometimes you do, depending on event-driven programming that you might be utilizing or other other applications in which it's thoughtful and you realize you need that. Most of the time it's an error when that happens. So within the while loop, within one of the statements that belong inside that while control statement or while construct, you want to change or mutate that value n so that eventually it'll result in a false when that Boolean expression is evaluated. And the syntax is the same thing. You use the keyword while, you specify the conditional expression within parentheses. That's what will evaluate to some Boolean value. You have a colon, and then you indent the statements that belong inside that construct. And so you can usually interchange between these two kinds of loops. So it's relatively easy to do. And in the for loop version, the loop variable was each number, and that automatically iterates over that sequence of values that's provided. So that's done implicitly there. Here you have to do it explicitly. So there we have it. These are the three fundamental control structures, and with these three control structures, and given enough time and memory, you can solve any problem in the universe that's computable. Enjoy. See you next time.